welcome back to my YouTube channel. Now in this video I'm going to show you on SPM F5 Physics Chapter 4 Part 2. It will be called Semiconductor Diode. Now previously I've talked about, in my part 1 of my video, I've talked about CRO, cathode ray oscilloscope, and this is one of the model that I use to show you how the filament work over here. You may click on this square and it will bring you another YouTube video on how the filament work. Then I'll make use of a nichrome wire, but this is not actually the real material because I believe they're using tungsten wire over here, but not nichrome. Nichrome is for other application. It's only for 350. For CRO you need relatively higher temperature, and then it will heat up a piece of metal and then provide potential difference, and electrons start to emit from the surface, and then that's what you have gone through in the past. So you would like to, I would advise you to look at my previous video to actually have an idea of how CRO actually work. So in this video we're actually talking about, we'll talk about semiconductor diode. Now before I really talk about semiconductor diode application, I would like to talk about semiconductor. Okay, what is semiconductor? Okay, let's answer the question. What is semiconductor? Now this video above here, this square, you may also click onto it because it will bring up another video that will compare conductor, compare semiconductor. This is actually a metallic silicon. Yes, I mean it's very much different than from the silicon that you have known of, because normally silicon has to be squeezy, or perhaps silicon has to be in plastic look, but this is a piece of metallic silicon. And then over your right, this is actually insulator. It's a piece of wood and also a piece of rubber. So I'm going to compare them in terms of electrical conductivity. You want to click on it and have a look what happened. Let's say this is a piece of aluminum and aluminum oxide aside, because the surface will have an oxide layer making aluminum oxide. That's why it doesn't contact. But at the edge, what happened, I used to cut it, it exposed the pure form of aluminum. That's why it's conduct. So you can actually tell if a material is shiny. It's not necessarily that it would conduct electricity or not conduct electricity. It is just a general guide, and it cannot be used to summarize, to tell that shining surface has to be electrical conductor. There's no such a theory. It has to be treated with care, especially when it deals with current. So you may want to look at it, and you'll be surprised that metallic silicon in this pure form doesn't actually conduct electricity. This is actually pure metallic silicon. I mean metallic silicon, M in front. Okay, so how do they get this piece of metallic silicon? I think doesn't need to elaborate more. As what you have learned from your chemistry, SPM, let's say you have silicon oxide, Si2O3 perhaps, quarks perhaps. So what it does, they remove the oxygen, so you get your silicon. Okay, so how they remove it, they will normally use, you add in carbon, maybe you use charcoal, coal, or perhaps they use actually wood, chips of wood to burn with the rock, and then eventually in a chemical process they were able to melt it off. The C and O combine, you get CO2, and then you left with your silicon. And then they melt it, they cast it, and then they eventually crush them into pieces. Then you may use it for other process to make a silicon wafer. Okay, so this is a piece of metallic silicon that I obtained from one factory to show you how does it look like, silicon. So to answer the question, what is semiconductor, because it doesn't really actually answer that question yet, right? Now semiconductor is made from silicon, or remember from group 14, is a material with resistance between the two, between the conductor and insulator. Okay, so between conductor, resistance between conductor and insulator. Okay, that's why it makes this material interesting. Okay, now if you care to use this piece of metallic silicon, scientists, actually not me, scientists, if you were to zoom in, okay, to zoom into it a few 100 times or 1,000 times, good enough to look at the molecule of silicon. Okay, so say for example you have silicon. When you zoom into that particular part, silicon arranged in the planar form. I mean, you zoom into here already. You zoom into here. Okay, so you see silicon arranged in a lattice form. Okay, I mean, lattice. You may want to Google what does it mean by lattice form. It's a repetition of how the atom arrange. And then for group 14, for example, silicon, they are going to have 4 electron valence. Okay, so this molecule have 1, 2, 3, 4, 1, 2, 3, 4. This 1, 2, 3, 4, and then the same goes with here, 3, 4, 1, 2, 3, 4, etc. Okay, so what happened? 4, 4. Okay, then it's another one belongs to the atom next to it. Okay, and then this belongs to another atom, and then this belongs to another atom, belongs to another silicon atom. Okay, so what happened? It will bound. It's actually being bonded, isn't it? It's being bond. Okay, it's being bond. Share, actually, electron valence. Okay, sharing of bond. In reality, there's no such thing. You can't really see it, but it is stick together because of this electron valence force. You can't really see it. There's actually no line to connect them. In reality, it's just a representation. So this is a representation graphic. It's not an actual graphic. Say it's being zoomed into it. Those lines help you to illustrate what happened. Okay, so if you really zoom into it a few 100,000 times under transmission electron microscope, perhaps. Okay, this is what happened. Okay, it's being bound together. Now, what happened? All the electron valence is actually being bonded to form a bonding. So what happened when you look into this video, you click into it, what happened? I use DMM to connect it. Say for example, if I were to connect them into a positive and negative for my video, positive and negative, what happened? It doesn't conduct, right? Let's say this is my one end. I sandwich this material with a positive and negative potential difference. Okay, what happened? Electron cannot pass through it. Reluctant to pass through it. Actually, it doesn't want to pass through it. I use DMM. I test one end, another end. What happened? It doesn't really have the click sound. It doesn't have the sound, say continuity, meaning it's connected. As compared to metallic, if I connect one positive, one negative, what happened? You hear the beep sound. Okay, kindly pause this video, click into this video, okay, into this square. Anywhere around this square, you will bring up another video, and then you will see that for metallic, either end, you click on it, then they have free electron. That's why electron will pass through it. That's why they will say this is electrical conductor. Okay, but whereas for silicon, semiconductor is a material considered a semiconductor. What happened? There's no free electron that allows another electron to pass through from one end to another. Okay, so how are you going to improve? How are you going to improve the conductivity? Why they say it's between the conductor and insulator? Okay, how are you going to make it to conduct? At certain point around here it conducts, isn't it? But another end it doesn't. Most probably because one of the lattice is being broken off, and therefore electron could be moved, drift from one end to another. That's why it conducts. Okay. So how to improve? Let's answer the question. How to improve the conductivity? Okay. In some over the internet, if you care to look into, there's a term called doping. Okay, doping is actually a process. You may want to copy down and make your own notes, and then you read on your reference, and it will be much more easier. Process of add something. Okay, adding a small amount of impurities. Yes, you don't like impurities. Yes, but in this case, you need impurities. Okay, so impurities is not necessarily always bad. What does it mean by impurities? Impurities will be those material that doesn't belongs to the major material. Say here, this whole piece of material is silicon. Impurities would be maybe you add in ferrum, or you add in aluminium into this piece of material. Then it will be, the aluminium would be an impurities. Now, what does it mean by small? Okay, small amount would be no more than about 10%. No more than 10%. Say for example, if this piece of material, it says you have 1 mole of silicon, then no more than 1% of aluminium. Okay, or maybe make it easier, 10 gram. 10% of 10 gram, that would be like, wow, that small. Okay, should be less than 10%. Okay, so this is what it means by doping. So what does it mean by that? You add amount. It doesn't really just add it. It is not that you sprinkle on the surface. It's not that. It is, you use this piece of material. Okay, you put in a furnace. Okay, this piece of material, drop it in. This is silicon. Then only you add in no more than 10% of actual weight of maybe aluminium. Melt them, blend them together. So that this is what it meant by doping. Compared to coating, it's not coating but doping. Okay, you small amount, you melt them and blend them together. Okay, so this would increase. Therefore it will increase its electrical conductivity. So how could you improve it? This is how. But of course, the percentage where you add in would actually affects the electrical conductivity. If you add more of it, then you will conduct more. If you add less, then the conductivity will be less. So now you realize I only mention conductivity and do not mention electrical, because in this chapter 4, we talk about electronics. So it's therefore in the future I will just mention conductivity for all this video related to Form 4 Chapter 5. So it's our common understanding means electrical conductivity, meaning electron would pass through it. Then how, when you add in a small amount of material, how is it possible that it would actually conduct? It's like this. What happened when you were to dope this material with aluminium? What happened? One of it would be lost. Maybe, oh, this is no longer silicon. Because remember, you melt them, then you add aluminium. So therefore, this lattice is now being replaced by aluminium. And aluminium doesn't have 4, but aluminium is group 13, so it has only 3 electron valence. So here, what happened? You have awakened. So you have 1, 2, 3. So this is actually a hole, a void or a hole. Okay. So therefore, what happened when I were to apply positive and negative source, terminal, anode and cathode, what happened? Electron could now flow through it, through the hole, and then you create a hole. Then eventually, electron pass through it, through the electron hole pair. Electron whole pair. Okay, that's why the electron could now conduct. Okay, so therefore the conductivity could be improved by either one, you introduce, or since you learned that word already, therefore we dope with impurities. There are certain rules. For example, it has to be small amount, less than 10%. Another rule has to be equivalent size. Okay. Then, I mean, what does it mean by equivalent size, right? Say for example, silicon. Silicon is actually group 14. Group 14. Okay. So equivalent size, the size, a diameter of this atom, pure form, along the periodic table. The size has to be the same if you were to be group 13 and group 14 and group 15, right? The one before and the one after. Then the shape and the size will be equivalent, correct? I mean, you need to literally relate this chapter with chemistry. Yes. Okay. Now, so therefore, if you were to dope with impurities, meaning if you add in impurities, this is no longer called a pure semicon now. This is therefore now called extrinsic. E-X-T-R-I-N-C-S-I-C. Extrinsic semicon. Okay. Why extrinsic? Because you add in foreign material or impurities to silicon. Therefore, it's now extrinsic semicon. Now, for extrinsic semiconductor, there are two categories. Extrinsic semicon. We haven't actually answered the question of semicon diode, but this would be the background behind it. Okay, so actually two types of it, which I think you have known by now. You haven't read through it, but if you have read through my video, then eventually it helps you with your reading later. Okay, so there are two types, as I mentioned. Has to be same. We talk about same shape, same size, isn't it? So if in the event, say for example, my silicon is in the middle, group 14. Okay, so those before, if you add in, you dope material from group 13. Okay, so therefore it would be a p-type. Say for example, group 13 we have what? We have boron. Introduce small amount of boron, indium. Now those material could be hazardous. You do not want to actually deal with it without special caution. Or aluminium. Okay, so those are the group 13. Whereas group 15, so group 15 could be antimony, could be phosphorus, or perhaps arsenic. That's why semicon could be dangerous, because they are hazardous material. For example, arsenic. Okay, so these are actually the hazardous material. Oh yes, antimony is actually Sebranium Sb. Okay, old name. Okay, but it's antimony Sb. Some may be pummeled, but as long as they are from group 15, therefore it will be n-type. Why is it n-type? N means negative. Negative. Why is it negative? Meaning because there are lots of, not lot, electrons, many, because this group, they are electron rich. They are considered electron rich. Why? Why is it so rich? Because for silicon, they are going to have only 4 electron valence, right? 3, 4. So for n-type material, they have 5 electron valence. So it's considered the n-type material. Whereas for p-type, they have only 3 electron valence. So if you were to dope it into the silicon, what happened? You have a deficiency of electron. That's why it's P. P is positive. Okay, so this is how it helps you to really get into mind. The p-type means group 13. N-type means group 15 because they are 5 electron valence. Okay, so if you were to add in n-type, what happened? The consequence, electron as the major charge, because you have more carrier than whole to be minority. Okay, the opposite will be for p-type. In this case, whole as the majority carrier, charge carrier, CAR, whereas the electron would be the minority. Okay, this is one of those objective questions. And then that's all about extrinsic semicon. Along there's some reference texts you come across with intrinsic semicon. Intrinsic. As I see, okay, intrinsic. Okay, intrinsic semicon, it's those material. I think it's better not to. It's not in the syllabus, so it doesn't really need to care about it. Intrinsic meaning it is only pure semicon, silicon. They will normally heat it up. Okay, shine light, heat it up, like what you have learned previous chapter. You heat it up, then therefore electron would start to conduct. Okay, those are the intrinsic behavior. They use heat as a source to move an electron from one end to another. Whereas extrinsic semicon, they use electrical potential. Okay, electrical potential, this is positive, negative, then electrical potential to push an electron from one end to another. So in order to do that, you need to dope it with an impurities. Okay, I think that's basically all about it for this video. I will talk about how do you get diode, yeah, in my next video. If it is the first time watching my video, kindly subscribe to my channel, and I appreciate those thumbs up. Stay tuned to my next channel.